Okay, YouTube, in this video we're going to be kind of a warm-up here to solving exponential and logarithmic equations. So we're going to be visiting a few of the properties of logarithms and exponential expressions here on the left. As you can see, I've kind of highlighted these. And just kind of show you how they're used in a basic sense to solve exponential and logarithmic equations, but then we're going to kind of move on and look at some more complex examples in my next videos where, honestly, I intend to spend maybe like 3 minutes or less on each video just showing how to do an example of each one. So let's go ahead and visit these equations over here, these properties over here, pardon me, of exponential and logarithmic things. Starting with 1 to 1. 1 to 1 is very, very convenient property, but it basically says this. Look, if you have two bases that are the same and they're equal, then their exponents are also the same. That is, if a to the x equals a to the y, well then duh, x has to be the same thing as y. So that's true if and only if x equals y, and likewise with a logarithmic expression, if you have two logs, notice here that they have the same bases. If they are equal, then the argument on each one is also the same thing, so x equals y. These inverse properties are very, very useful, and you see them often. We're actually going to use those, but without going too much into the details of it, what we know is this. If we said a to the power of log base a, so the important thing here is this. Our base of our exponential expression is the same as the base of our exponent that has, a log of base a. That is, these two bases are the same. Then this a to the power of log base a, they cancel each other out, and what's left is x. And likewise, we say, well, if I had like an exponential expression like a to the x with base a, if I were to take the log base a of the exponential thing with the same base, then log base a and a would cancel each other out, and we'd just be left with x. So that being said, let's jump right into a few where we would start by using, say, the 1-to-1 property, starting with something like this. What if we had, for example, call this example A, we say 2 to the x. We like powers of 2, so 2 to the x is equal to 512. Now I say this is 1-to-1 because if you recognize that 512 is actually a power of 2, if you're a computer nerd or something like that, or you're just a normal person who recognizes that it's a power of 2, you could say, well, is there any way I could rewrite these to have the same base? I noticed that the base over here on the left is 2. Could I make this 2 to the power of something on the right? And as a matter of fact, the answer to that is yes. So we say 2 to the x. This is the same thing as 2 to the 9th power, and you can check my math on a calculator. I've done this on purpose, but if this is the case, we say 2 to the x equals 2 to the 9, then what we could do is just jump straight in and say, well, then x must be 9 because of the 1-to-1 property. Okay. Moving right along, what if we had something that was a little bit more obscure, but we say the natural log of 5 minus the natural log of x, and we'll say that this equals 0. Okay, now a couple things real quick. Remember the natural log, when we write the natural log, we're just saying the same thing as log base e, okay, or the natural log base of 5 minus the log base e of x equals 0. But since we want to use 1-to-1, what we'll do is we'll just take, say, log or natural log of x and kick it over to the other side. So we end up with ln of 5 is equal to ln of x positive, and we say, okay, well then if this is the case, 5 equals x or x equals 5. But just know that, if you're going to use 1-to-1, you have to have things on either side of the equation. Moving right down the road here, if we had something, for example, 1/5 to the x, we can play around with negative exponents here. 1/5 to the x is equal to 125. One thing we could recognize is this. We could say, well, if I want these to have the same base, necessarily 5 is kind of the number I'm playing at here, because I know I have 5 and then it's in the denominator over here, and I know that 125 is a power of 5. So we're going to start with this 125 on the right here. We know this is 5 to the power of 3. And over here on the left, this is the same thing as kind of 1/5 to the positive x. So two things we can do here. We can either take this 5 and put it down here in the basement, and it would become this expression. 1/5 to the positive x equals 1/5 now to the negative 3. And this would be 1-to-1, where in this case x would be the same thing as negative 3. Whoops, negative 3. And I'll make that 3 a little bit prettier. But we could also have done it this way. We could have said that 1/5 to the x, okay, or basically is the same thing as 5 to the negative x, and brought that back upstairs and said that's the same thing as 5 to the 3. But then we'd say, okay, well then 1-to-1, this negative x has to be the same thing as 3, therefore x is negative 3. So those are a few examples of 1-to-1. So let's take a look at just a real quick view with the inverse property, because this is the meat and potatoes of it all. But if we said, all right, so D, if we had some expression said e to the x equals, say, 13, and this isn't going to come out to be pretty. We're actually going to need a calculator in our change of base formula. Oh, not on this one, but we'd say, okay, so now I want you to notice this. If I'm going to solve this exponential thing, the interesting thing is to undo an exponential expression, which is our first property over here on the left, to undo an exponential expression or a logarithmic expression, wow, I'm sorry. To undo an exponential expression, we're going to use the second property down here on the left. But basically, we've already isolated the exponential thing on the left side of this equation. So we're going to use a logarithm to undo this exponential thing. It's just that I want to take the log of both sides, since this is an equation, and I want to take a log base e. The reason why is because in order to get our inverse property to work, we have to take log base e of base e to the x. And we have to do the same thing to the right-hand side of this equation. So log base e of 13. So now, honestly, I would never really write it like this, but I know this log base e and this e to the power of that cancels those e's out, and I'm left with x. What I really would have written if I had done this for reals is ln of e to the x. Okay, is the same thing as ln of the stuff on the right, which was 13. And so we get ln and e to cancel out, and we're left with x equals ln of 13. And the convenient thing here is this. We could just flip over to a calculator that has a natural log on it. So we say ln 13, enter, and we get e to the power of 2.56-ish. So x is approximately 2.56-ish. Okay, so there's a convenient example of how to solve, like, say, an exponential expression using a log. What if we started with a logarithmic expression? So what if we started with, like, ln of x, and we'll call ln of x equal to -8. So to undo this logarithmic expression, we're actually going to use an exponential expression. This is kind of an odd thing to do, but what we're going to do is what we call exponentiating both sides. So to exponentiate, that means to make both sides the exponent of some exponential expression. So I'm going to say this. I'm going to say, well, since this is ln, or log base e, I'm going to exponentiate both sides with base e. So I'm going to say e to the power of all of this is the same thing as e to the power of all of this, because e to this equals e to this, then 1 to 1 says then our original expression, ln of x equals -8, is still true. The reason for doing this is because of our first inverse property over here that says this. A base to the power of log with the same base, that base and the log with the same base cancel out, and you're left with just x. And that's equal to e to the -8, which, we can type this into a calculator, and we will in just a moment, but I want you to recognize this. The original expression was ln of x, or log base e of x was equal to -8. So really, the expression we just turned out was really the same thing as if we took our base here, which was e to the what power turns it into x? Well, e to this power turns it into x. So e to the -8 turns it into x, which is really the same thing that we found here using our inverse property. So e to the -8, we'll just pull out the calculator here. Whoops, clear. So we got e to the power of -8. And we get, 3.354 times 10 to the -4. So about x 0.0003-ish. Okay. But anyways, this is a real quick run through on how you'd use your inverse properties and one-to-one properties. We're going to run through some more examples here in the next few videos.